Today I want to tell you how we can bound the probability that a random variable is too far away from its mean value. These go by the name of tail inequalities and include things like Markov's inequality and Chebyshev's inequality. As always, let's start with a story. For the coming battle, the king expected the vassal to send on average 100 archers to bolster his army. The king wondered, given this information, what was the largest the chance could be that the vassal would send at least 300 archers? One way to view the expected value of a random variable is to think about carving the density out of wood. Then physically, the value mean of x is the point where if a fulcrum was placed underneath the density, it would balance exactly. The shaded region over 0.75 to 1 in the figure above has area equal to the probability that x is greater than or equal to 0.75. An event of the form x greater than or equal to a for some a is called a tail, or more specifically a right tail or upper tail event. Given that the fulcrum, that is the expected value, for the density in the figure is 0.4, the area of the right tail cannot be too large, or the figure would tip over when made in real life. This idea that the right tail cannot be too large given the expected value of a random variable goes by the name Markov's inequality. Markov's inequality says that for an integrable random variable x and a greater than 0, the probability that the absolute value of x is greater than or equal to a is at most the mean of the absolute value of x divided by a. Note that the theorem deals with a non-negative random variable absolute value of x. This is because if the right tail can be balanced with the left tail that is negative, the expected value does not prevent the right tail from being arbitrarily close to 1. But if the random variable cannot fall below 0, then the inequality holds. The proof is fairly simple. The key idea is that for any positive numbers, x and a, x times the indicator that x is greater than or equal to a is itself greater than or equal to a times the indicator that x is greater than or equal to a. To see why this is true, first suppose that x is less than a. In this case, both sides are 0. So 0 is greater than or equal to 0. If x is greater than or equal to a, well, then the indicator functions are both 1, and we just have the inequality x is greater than or equal to a. Now also, since both x and the indicator that x is less than a are at least 0, the product x times the indicator that x is less than or equal to a is also greater than or equal to 0. With these inequalities in mind, the proof of Markov's inequality is as follows. Let a be greater than or equal to 0. Then the absolute value of x equals the absolute value of x times the indicator absolute value of x is greater than or equal to a, plus the absolute value of x times the indicator that absolute value of x is at most a. That's greater than or equal to a times the indicator that the absolute value of x is at least a. Taking the expected value of both sides gives it the mean of the absolute value of x is greater than or equal to a times the mean of the indicator that absolute value of x is greater than or equal to a, and the mean of an indicator is just the probability that the thing inside the indicator happens. So this is just equal to a times the probability that the absolute value of x is greater than or equal to a, and rearranging gives the result. In the story, let a denote the number of archers sent by the vassal. The king knows that the mean of a is 100 and wants an upper bound on the probability that a is at least 300. Since a is greater than or equal to 0, the absolute value of a is just a. From Markov's inequality, this gives the probability that a is at least 300 is at most the mean of a divided by 300. So 100 over 300, or 1/3. So the king upper bounds the probability by 0.3334, rounding up the last digit in order to ensure an upper bound. Now, for this problem, the last digit of the probability was rounded up. And this is because the goal was to find an upper bound on the value. If the goal had been to find a lower bound, then the value would have been rounded down. Now, Markov's inequality seems so simple, but it is the basis of many other important tail inequalities in probability. One such is now known as Chebyshev's inequality. Now, Pafnuty Chebyshev was actually Andrei Markov's teacher. Chebyshev was the first to create what is now called Markov's inequality. So sometimes Markov's inequality is called the first Chebyshev inequality, and Chebyshev's inequality is called the second Chebyshev inequality. This inequality gives an upper bound, which is usually, although not always, better than the straight Markov's inequality. Moreover, it gives a bound on the sum of the upper and lower tails. And it works on random variables. They are both positive and negative. The idea is to apply Markov's inequality to the new random variable, which is x minus the mean of x, quantity squared. Recall that the mean of this variable is the variance of x. So for x, an integrable random variable with finite standard deviation, and a greater than 0, the probability that the absolute value of the difference between x and its mean, the probability that that is greater than or equal to a, is at most the variance of x divided by a squared. The proof uses Markov's inequality. The probability that the square of the quantity x minus its mean is at least a squared is at most the mean of the quantity x minus its mean squared, all divided by a squared. The numerator is just the variance of x. Then we just use the fact that in order for the square of the difference between x and its mean to be at least a squared, it must hold that the absolute value of the difference between x and its mean is at least a. For example, suppose that we have a random variable t with mean 15 and variance 25, and we want to upper bound the probability that t is at least 25 using Chebyshev's inequality. Well, the event that t is at least 25 is the same as the event that t minus 15 is at least 10, and that event implies that the absolute value of t minus 15 is at least 10. So the probability that t is at least 25 is at most the probability that the absolute value of t minus 15 is at least 10, and that's at most the variance of t divided by 10 squared by Chebyshev's inequality, which is 25 over 100, so 25% is an upper bound on the tail probability. You can also phrase Chebyshev's inequality in terms of how many standard deviations away from the mean the random variable is. Suppose that a random variable x has a finite standard deviation. Then for k greater than or equal to 1, the probability that the difference between x and its mean is at least k times the standard deviation of x is at most 1 over k squared. For the proof, just plug a equals k times the standard deviation of x into Chebyshev's inequality and simplify. Recall that the sample average of the first n values of x sub 1, x sub 2, etc. that are IIDx, where x is an integrable random variable, is s sub n, which is x sub 1 plus x sub 2 plus up through x sub n divided by n. The strong law of large numbers indicates that with probability 1, s sub n will converge to the mean of x. But it does not tell us how quickly the convergence occurs. Now, unfortunately, Markov's inequality does not improve for sample averages as n increases. The mean of s sub n is the same as the mean of x, so the probability that s sub n is at least a is at most the mean of s sub n over a, which is just the mean of x over a, and there's no n on the right-hand side. On the other hand, if the variance of x is finite, then Chebyshev's inequality does improve as n grows. Let x sub 1, x sub 2, etc. be IIDx with the mean of x equaling mu, the standard deviation of x equaling sigma. S sub n being the sum of the first n values of the x sub I, all divided by n, then the probability that the absolute value of S sub n minus mu divided by sigma is greater than or equal to k is at most 1 over n times k squared. For the proof, recall that the variance of a sum is the sum of the variances when the random variables are independent. Because we're dividing by n, the variance gets divided by n squared. The result is n over n squared times the variance of one of the x sub I, and that's just the variance of one of the x sub I divided by n. Hence, when we put that into Chebyshev's inequality, the probability that S sub n minus mu over sigma in absolute value is at least k is the probability that the absolute value of the difference between S sub n and mu is at least k times sigma, and that's at most sigma squared over n times the quantity k sigma squared, and the sigma squareds cancel out to give 1 over n times k squared. For instance, if a sub 1, a sub 2 are IIDA, and S sub n is the sample average of the first n of the a sub I, for a with mean 3.2 and standard deviation 1.6, how large does n have to be before the probability that the sample average is at least 4 is at most 0.1 using Chebyshev's inequality? Well, using S sub n as the sample average of the first n of the a sub I, and we can standardize S sub n, recalling that it has mean 3.2 and standard deviation 1.6 divided by square root of n. So the probability that S sub n is at least 4 is the same as the probability that the standardized version of S sub n in absolute value is at least 4 minus 3.2 divided by the quantity 1.6 over the square root of n. We can simplify that expression and then invoke Chebyshev's inequality to say that the probability that S sub n is at least 4 is at most 2 over square root of n squared, which is 4 over n. Setting 4 over n to be at most 0.1 gives that n needs to be at least 40. Now, usually the goal of using a sample average is to estimate the mean value of a random variable. Often, the relative error is required. The relative error in estimate hat A for A is the absolute value of hat A over A minus 1. For instance, if the true answer is 3 and the estimate is 3.3, then there is an absolute value of 3.3 over 3 minus 1, or 10% relative error in the estimate. Now consider bounding the probability that the relative error in the sample average as an estimate of the mean is larger than some fixed epsilon. Using that the absolute value of the product is the product of the absolute values tells us that the probability that the relative error in the sample average is at least epsilon equals the probability that the absolute error in the sample average is at least epsilon times the absolute value of mu. That's at most sigma squared over n divided by epsilon times the absolute value of mu, quantity squared, and simplifying gives us that this is 1 over n times epsilon to the minus 2 power times sigma squared over mu squared. The last factor, sigma squared over mu squared, is unitless and is given the name relative variance. The square root of the relative variance is called the relative standard deviation, or coefficient of variation. For a random variable with non-zero mean and finite variance, the relative variance of x is the variance of x divided by the square of the mean of x, or you can think of it as the expected value of the square of x divided by the first moment of x squared minus 1. Then the relative standard deviation, also known as the coefficient of variation, is the standard deviation of x divided by the absolute value of the mean of x, and it's the square root of the relative variance of x. So Chebyshev's inequality says that to get a non-trivial bound on the probability that the relative error of the sample deviation is large, the number of samples must be inversely proportional to the square of the relative error and proportional to the relative variance. That is, n is big theta of epsilon to the minus 2 times the variance of x divided by the mean of x squared. A look at how the central limit theorem behaves gives a similar result. And this idea is often called the Monte Carlo error bound and represents a hard limit on how well sample averages can estimate their mean. So those are the tail inequalities. Markov's inequality and Chebyshev's inequality allow us to bound the probability that a random variable is too far away from its mean. See you next time.